Hi, we present our work, Inside Out, Measuring Generalization in Vision Transformers through Inner Workings. In this work, we target the problem, model evaluation without label. There are two benefits if we can do this. Before deployment, we can do model selection, and after deployment, we can raise alarm when models silently fail. To achieve these goals, the central question is how to evaluate model without label. Previous works introduced the accuracy on the line phenomenon that a model's accuracy in source distribution strongly correlates with its accuracy in the target distribution, which means you can select the model according to its source performance. Other works find that the model's softmax confidence also correlates with the model's performance. However, all of these metrics fail under certain scenarios. The accuracy on the line metric suffers from the issue of underspecification, whereas the confidence-based metrics are limited by the model overconfidence. So why are these existing metrics unreliable? Summarizing the commonality among these methods, they only look at the model's output, which is an indirect signal. So can we evaluate model generalization from its internal? Our work answers this question by developing an internal view which extracts direct signal of why model fails from its internal. The proposed framework is two steps. First, given the model and target data, which is unlabeled, we extract the model's inner workings. Step 2, we define the proxy metric based on the inner workings. We follow the circuit discovery method in mechanistic interpretability research to extract the model's inner working. Given the computation graph of a transformer model, the circuit discovery method assigns importance weights to each edge in the graph, which represents the causal relationship between the model components. Then we define a proxy metric based on the extracted circuits. For pre-deployment scenario, we use the source training data to train a model zoo, then test them on the target data. We start by visualize circuits of these models with the question, does weak model circuit look different from strong models? We visualize the three models with generalization performance ranked from weak to strong. We observe a pretty obvious trend. The weak model circuits are heavier at its shallow layers, while the strong model circuits are heavier at its deep layers, which means deep connections instead of shallow ones predict the strong generalization. Then we analyze the structural trend statistically across different datasets. In the previous observation, the trend appears to be layer-wise, so we first aggregate the circuit by layers. This results in an interlayer connection matrix. Then for all models, we apply the canonical correlation analysis, which gives how each entry in ICM correlate with true performance. This returns a matrix of the same size, which we call the generalization motif. Finally, we average GMs across all datasets, which gives us the universal generalization motif. The resulting pattern remains consistent with our previous observations. The upper right region is dominated by positive values, indicating that deep layer connections are generally pro-generalization. The lower region is mostly negative, suggesting that shallow layer connections, including shallow to deep shortcuts, are anti-generalization. With this analysis, we define our first metric for the pre-deployment stage, the DDB metric. Because we want the metric to be maximally correlated with the performance, we simply define DDB as the positive correlation part divided by the negative correlation part. We also define three variants of DDB by choosing different target layer range. As a result, DDB metric mitigates the underspecification problem, and quantitatively, we evaluate the metric on three datasets with different distribution shift types. The best DDB variant achieves an average correlation score of 0.766, which is an 13.4% improvement over the best baseline. For the after deployment scenario, we test the deployed model on a distribution zoo, where we also begin by visualize circuits with the question, how circuit change as distribution shift gets more severe. We extract circuit on a model D under the source distribution and increasing distribution shifts. We observe that the overall structure doesn't change much, but it exhibits increasing rewiring on the larger distribution shift. To explain this phenomenon, we hypothesize that the circuit of a model will not change its structure drastically, but gradually drift away from source circuit. Based on the hypothesis, we define our second metric after deployment, circuit shift score. Given a circuit space R and a distance function d, the CSS metric is the distance between the source circuit and the target circuit. We instantiate the circuit representation space R in two ways: graph space, where circuits are represented as weighted graphs, and vector space, where circuits are flattened into vectorized edge weights. And for each space, we also tested different distance metrics. The qualitative result shows that CSS significantly mitigated the overconfidence issue. We also quantitatively evaluated CSS on 4 datasets, which shows the best CSS variant achieves 34.1% improvement over the best baselines. In conclusion, we demonstrate that a model's internal circuit structure provides a reliable signal for estimating its performance on the distribution shift. We introduced two circuit-based metrics, DDB for pre-deployment model selection and CSS for post-deployment model performance monitoring. Both metrics substantially outperform existing proxy metrics. Together, these results establish a new framework for leveraging a model's internal mechanism to predict its behavior on the distribution shift. That's all. Thank you.